let's let's try to understand the concept of phase difference. Phase difference. The concept of phase difference appears in many topics of physics like interference, diffraction, oscillations, AC theory, and all such places we come across with the idea of a phase difference. To understand phase difference, we consider a simple harmonic motion. We consider simple harmonic motion. Simple harmonic motion. A simple harmonic motion is usually discussed or studied by considering a circle. These are the two diameters. The point A, B, Z, D. Just imagine a point P that revolves along the circle. P moves uniformly. P moves uniformly along the circle. Suppose this angle is theta. This angle is subtended at time t. So angular velocity omega is equal to theta by t. Therefore, theta is equal to omega t. So this theta is equal to omega t, where omega is the angular velocity of uniform circular motion. Now this is the foot to the perpendicular drawn. I am calling it as a PM. So M is the foot to the perpendicular. This is the origin. Now let's see, as P moves from A to B, M moves from O to M. As P moves from B to Z, M comes back to O from B. As P moves from C to D, M moves from D to O to D. And as P returns to A, M moves back to O itself. So when P makes one rotation, the point M makes one oscillation about O. This is the point M and this is the point P. So I show like this. Now let's plot the displacement in this graph. Displacement on this way. This is the maximum displacement. This is 0. This is pi by 2, pi, 3 pi by 2, and this is 2 pi. Okay. So as P makes one rotation, the point make one oscillation about O. Similarly, we get one cycle here, one cycle of wavelength lambda. And the period of rotation is t. So all the four quantities are equivalent. When the particle P makes one rotation, the angular displacement is 360 degree, and it is equivalent to 2 pi radian, and it is equivalent to a period, that is t. When particle Pm makes one rotation, oscillation, the time is t, and a cycle, this is called a cycle, it advances a distance lambda. So all the four quantities are equivalent as far as the simple harmonic motion is concerned. Now let's understand what a phase is, what exactly a phase is. For that purpose, I take another situation. Here the particle is already displaced to some angular displacement phi, and in time t, displacement is omega t. So the total angle is omega t plus phi, and this is the displacement y. Then this amplitude is a equation gives sine omega t. Y is equal to a sine omega t plus phi. Y is equal to a sine omega t plus phi. Here the equation is a bit different. Here this is amplitude a, and this angle is theta. This is displacement y. The equation is y is equal to a sine omega t. Here. And in this situation, this is very general. We use y is equal to a sine omega t when the particle crosses equilibrium up at t is equal to 0. This is very general. The particle has a initial displacement phi. The quantity of phi is called initial phase. And omega t plus phi is total phase, or simply phase, total phase. Now we see the value of phase and its state. So here comes omega t plus phi. Here we consider the state or phase. When omega t equals, when omega t is equal to 0, our phase state will be O, the particle crosses equilibrium. When omega t plus phi is equal to 0, the particle crosses equilibrium position in the upward direction. When omega t plus phi is equal to pi by 2, the particle reaches the maximum displacement B. When phase angle omega t plus phi is equal to pi means it comes here, pi. In that case, the particle crosses equilibrium but down. When angular displacement or phase omega t plus phi becomes 3 pi by 2, the particle reaches the position D, and when the total phase becomes 2 pi, the particle comes to O but moves up. So these are opposite. So by knowing the quantity omega t plus phi, we will be able to guess the state or the particle at any instant t. So this quantity omega t plus phi is called phase, and this is a very general equation for simple harmonic motion. This is restricted equation in the sense we use this equation only when the particle crosses equilibrium O at t is equal to 0. This is very general. The particle could be anywhere else. In this diagram, the particle has already displaced. This is the initial position of the particle, initial position. At t is equal to 0, this is the displacement, initial displacement. After that, we count, we reckon the time. That's what this is the phase relationship. Now we understand the phase difference. For that purpose, we consider a simple pendulum. This is the equilibrium position, and the bob is at the maximum position 0 degree, 90, 180, 270, 360. So this angular position theta is equal to 90 degree. Now think of pendulum all the same length, but here. So the particle is at equilibrium position. Here theta, we take theta 1, this is theta 2 is equal to 0 degree. So what's the phase difference? Theta 1 minus theta 2, phase difference is equal to 90 degree minus 0 degree is equal to 90 degree. That is a phase difference. Now second example. Now the bob is at the right extreme. So theta 1 is equal to 90 degree. Here the bob is at the left extreme. Then angle is theta 2 is equal to 270 degree. So phase difference is equal to larger minus smaller. So 270 degree minus 90 degree is equal to 180 degree. It is called opposite phase. One bob is at right extreme, the other bob is on the left extreme. So this is the opposite phase. And we can visualize this phase difference like this. This is the same phase. This is one particle, this is the other. Same phase. Both the particles reach the maximum at the same time. They come to the equilibrium simultaneously. They reach the negative maximum simultaneously and return the equilibrium point simultaneously. So this is same phase. At times we call it as the particles are in phase. The 90 degree phase difference. Here one particle is at equilibrium, the second one is at maximum. 90 degree phase difference. Like this. Then opposite phase, one is at top 180 degree, the other is the one is at the maximum, it's at 90 degree, the other is opposite 270. So this is opposite phase. Two particles are executing SHM in opposite phase. This is opposite phase situation. There is a reality for this one. See here, this oscillation can be represented here. So the spring block system, we pull the block to the position D and then release. The block will make up and down oscillation. This oscillating block will lead to this type of situation. See here, the center of the block is represented as point M. So as the block moves up and down, the point M moves up and down along the diameter of the circle. It is the circle is called a circle of reference. Circle of reference. And we study the simple harmonic motion by examining the behavior of the point P along the circle. So we consider a uniform circular motion. So SHM is always connected with the uniform circular motion. By considering the uniform circular motion, we obtain the equation for displacement and all the related quantities. Let's conclude like this. When P makes one rotation, M makes one oscillation. Meanwhile, one cycle is produced in the medium. And two particles executing SHM will have different states. The state of the particle executing SHM is given by the quantity omega t plus phi, the argument of the trigonometric function omega t plus phi. By knowing the value of omega t plus phi, we will be able to understand the location of the particle at any instant. This is the situation corresponding to a 90-degree phase difference. 90-degree phase difference is called a quadrature. There is a situation where we deal with a capacitor. When a capacitor is connected to AC, a quadrature occurs between the voltage and current, as we see now. This is the case of opposite phase. Now let's consider an example of a capacitor connected to AC. Capacitance C, voltage AC voltage is V is equal to V0 sin omega t. Current I is equal to dq by dt. Current I is equal to dq by dt, d by dt of q is equal to CV. That is C constant comes out. V is equal to V0 sin omega t. So d by dt of V0 sin omega t. Derivative of this is V0 constant. Derivative sin omega t is cos omega t. Cos omega t into omega. V0 by 1 by omega c. Cos omega t can be written as a sin omega t plus pi by 2. This is the maximum current I0 sin omega t plus pi by 2. The quantity 1 by omega c is called a capacitive reactance. See the waveforms of voltage and current waveforms. Sine waveform, voltage waveform is sin omega t, and current is sin omega t plus pi by 2. So there is additional phase pi by 2. So current is leading ahead of voltage by phase angle pi by 2. Let's see the waveform. This is the voltage and this is the current. This is the current waveform. This is the voltage waveform. This is pi by 2, pi, 3 pi by 2. This is 2 pi. Here we plot omega t. Here voltage or current. Now the current appears first. The peak of current appears first. Then voltage appears later. We identify a quantity which leads in a particular situation by noting the appearance of its peak. Here the peak of current appears first. Therefore current is leading. The angle is pi by 2. Here. So current is leading ahead of voltage by current is leading ahead of voltage by 90 degree or pi by 2 radian. This is obvious. Now when we connect a capacitor to AC, the current rushes to the plates. So initially the current is maximum. So capacitor will take some time to build up its charge to maximum value. So voltage becomes maximum after a delay. So current comes maximum first and then voltage. So current is leading ahead of voltage. The reason is obvious. By connecting capacitor to AC, the charges rush to the plate. So the current is maximum. But after some time, the charge builds up in the capacitor and voltage becomes maximum in a delay. And now we see the leading and voltage in general case. See, here there are two graphs. So one waveform is this one, the other one. Two waveforms are shown here. We will check which waveform is advancing or leading. What we have to do is just see which waveform comes first. This waveform gives its peak first than this one. The waveform 1 gives its peak with the shortest time. The peak of second wave comes later. This angle is theta 1, this is theta 2. First point, waveform 1 leads ahead of waveform 2. So waveform 1 is leading, or it's equal to say that waveform 2 is lagging, and with the phase difference is equal to this angle theta 2 minus theta 1. Thus, in general, if we have two waveforms, then identify the appearance of their peaks. The waveform whose peak appears first is leading and the other one is lagging. The phase difference is calculated by noting the difference between the angles. Here in this case, theta 2 minus theta 1 is the phase difference. Then we introduce the concept of phase shift. Now we noticed earlier that a phase shift of phase angle 2 pi corresponds to a phase angle 2 pi corresponds to a wavelength lambda. Therefore, this quantity is called a phase shift for unit length. It is denoted by k or beta times we use beta. In engineering, we use beta, and physics textbook we use a quantity k. K is called wave vector, magnitude of wave vector. This k. So k can be ended with phase shift. Say if this is a waveform, you move unit distance along the wave. When we move unit distance along the wave, along the axis, then the shift in phase is called 2 pi by lambda and is called phase shift constant. Suppose we move a distance x, then the phase shift corresponding to that part is 2 pi by lambda is for unit distance. Therefore, the phase shift phi for a distance x is equal to 2 pi by lambda x, or it is called kx. And if there is a phase shift here at the beginning, if this phase shift is phi, this phase shift is supposed to comes about phi, then the total phase shift is kx plus phi. And you recall that equation for wave y is equal to a sine kx plus phi. Here the quantity kx plus phi stands for the total phase. This is a very important quantity in wave analysis, phase. Now, conclusion: if you have two waveforms, identify the appearance of peaks. The wave whose peak appears first is leading. Of course, the other one is lagging. The phase difference between the waves is obtained by taking the corresponding angles, difference of the corresponding angles. In this case, peak of wave 1 appears at angle theta 1, peak of the second wave appears at theta 2. The phase difference is theta 2 minus theta 1.